Yes, it's pretty much embedded, right? Because you need a processor. So traditionally, you always require a MCU or DSP, right? So now, because the processing requirement is higher, you need to process a lot of videos and audio signals. You need to decide, for example, you have a lot of sensors in the car, you need to make decision on the brake and the steering and all those stuff. So the microcontroller approach is not very effective now, or you need many microcontrollers. So people are turning to FPGA. Not only that, FPGA have DSP and processing capability, but also because FPGA is programmable, so they can make changes very late into the design cycle. In actually one of the European car, right, like Mercedes-Benz, they have as much as 18 FPGA, Xilinx FPGA in one car. So it's a very good example of increasing use of FPGA. But now it's mostly in high-end car. But even for Hyundai, they also looking at using FPGA for some mid-range application as well. So it's going to be more and more common. It is one of our stronghold, actually. I would say strong. Our product, automotive product, is very strong. We have what we call the XA product line, Xilinx Automotive XA, which means that all our FPGA are qualified for the automotive standard. I think it's exceeding. I forgot the name of the standard. I think it's called the AEQ100 or something like that. I can double check. Don't quote me on that yet. I forgot the name of the automotive standard, but there's an automotive standard. I think that Xilinx is surpassing. Yes, we do have a pretty significant portion of the business. It's a double-digit, I think, percentage in our revenue. But our majority of the revenue, I think, like 45%, is still communication. Yeah, and then the next big section is ISM. I think it's coming up. It's especially in the past, most of these automotive activities in Europe or North America, because their design center is over there. And nowadays we see that they start moving. For example, like Delphi, which is a big U.S. company, right? They start recruiting, hiring a lot of people in China. So we can see that they are moving some of the design to China. Yeah. So this is the trend, right? Because China is already the biggest market for automobile in the world, right? They already passed America. So in the future, I think they will have more design over here. And also, I think the very successful Korean car manufacturer, Daewoo, Hyundai, right, Kia, these companies actually are also increasing their electronic contents in the car. FPGA already have crossover with embedded many years ago, right? If you look at our existing FPGA today, we already have 8-bit MCU. We call it Pickle Blaze, which is a Xilinx proprietary MCU. And then we have the 32-bit version of that. It's called Microblaze, MICROBLAZE. Microblaze has been as a soft core, has been used pretty common in our customers. And Xilinx also provided a set of tools called Embedded Design Kit, EDK, which is provide a one tool environment for embedded designer. So when they purchase our software tool, if they selected embedded design option, so the designer will get every tool from debugger to all the simulation tool, design environment, simulate everything into the environment. So embedded is not new to FPGA. Also in the high-end side, Xilinx have PowerPC in our Vertex family for 2 generations, right? So we have seen embedded has been a very important part of our FPGA. But moving forward, I think early this year in April, Xilinx has announced a new embedded strategy, which is what we call the extensible processing platform.
Extensible
processing platform, EPP, right? So these platform actually will include 2 ARM Cortex-A9 core plus all the peripherals, right? In the past, we do not have the peripherals, but now we will have, all the USB, the PCIe, the I2C, the UART, all the peripherals also standard in the FPGA, and it's a very powerful embedded system because the ARM core A9 is a very mid to high end core, right? It can run at 800 megahertz. So we have 2 in every single device.
So that's the combined ARM and other peripherals on a package level or die?
No, single die. It's a single die, monolithic die.
Okay.
And the ARM and the peripherals is hardcore, and then the FPGA is a soft. The advantage of that is you can still allow the FPGA to allow you to expand beyond a processor can provide. That's why we call it extensible processor platform. But there's a major difference between this and what's in the past, because in the past we also have processor core and FPGA fabric, right? But what are the major difference? It's because in the past it's FPGA centric, which means in the FPGA in the past you have to boot up the FPGA first before you can use the microprocessor. Now in the new EPP solutions is processor centric. In other words, even though the FPGA is not power up, you can still use the processor standalone. You can use it like a standalone processor. It has its own IOs, it has its own interface. The FPGA in the EPP is only a slave. The ARM is the master. So the ARM will control everything, including the FPGA. But versus in the past, I think some of our competitors also have FPGA plus ARM product. But the problem with that is the FPGA is the master, the ARM is the slave. So, which is opposite to most of the embedded design environment.
So, from the end user's point of view, what does the kind of reverse role of the FPGA and microprocessor make difference?
Oh, big difference. First of all, if you have an ARM on your PCB and an FPGA next to it, you need a lot of connection between the ARM and the FPGA, which means you use a lot of IOs. There's 2 reasons to put it in one chip. One is you reduce the number of IO so that you can use those IO for other user applications. Second is the latency. The latency between the IO of the FPGA and the IO of the ARM is very high. But if it's in one die, it's on chip, the latency is very short.
The high speed.
Very high speed. You can do a lot of things, right? So the FPGA can be used as a hardware accelerator for the ARM, right? So that's the beauty of it. And I forgot to mention that the chip also have like a hard memory controller. So you don't need to use FPGA to build those hardware memory controller anymore. The other beauty of that is because FPGA also have DSP blocks, right? This is basically the nature of the FPGA. In other words, you can look at the system, one chip. You can have ARM, you have FPGA general logic, you can also have DSP. So it's all 3 in one device. The DSP will create a tremendous processing power. Example like matrix multiplication, matrix inversion, or video processing. Those are very, very powerful features, which, for example, a traditional ARM core does not offer that. So it's almost like you're putting a TI, DSP, and an FPGA and ARM all in one chip, right? So, and it's programmable, right? So I think that's what we see that, to your question, because of this new breed of the product, we think we can allow Xilinx to go into embedded market to the area that we've never been before. Either is automotive, right, or is digital camera like consumer, or LCD display. You can also go into communication like wireless, right? We're talking about femtocell, enterprise femtocell. We're talking about baseband. So communication, they also need ARM core to do some monitoring functions, right? So now it's all in one chip. We can also go into like audio video broadcast, right, which you need a processor as well. You can also go into some high-end industrial surveillance, right, or medical imaging. So the application is definitely very promising for a product like that. So now we have not announced the name of the family. We just announced the platform. So our next step, we're going to announce the family next year.
Specific.
Yes, specific like devices and other. What's the capability? Yeah.
So that the EPP is the uniform platform.
Yes.
And based on that platform, you can develop.
Many type of products.
Many very specific application product.
Yes, and this is going to be based on our Series 7 technology. Right, which is 28 nanometer process technology. Yes, and you will have high-end part and low-end part. It will be a full, family. Very good point, DJ. The traditional embedded system, we can look at the mainstream. I would call it mainstream embedded system. We are all focusing on the 8-bit, 16-bit, and 32-bit microcontroller area. Those areas could be also our target, but the Cortex A9 may be too powerful for those markets. Maybe ARM 9 is enough, right? So right now, Xilinx choose Cortex A9. The reason is we want to serve the segment who require significant processing power, or which also give a pretty good leverage to our current FPGA technology. For the traditional very low-end embedded environment, we have to look at what will be the best value to this market, right? For example, the requirement will be very different. They do not need a very high powerful ARM core. Second is they probably need a very low standby power, right? And they need it very cheap. Right, maybe in the sub $5 range, right? So those areas, right now we do not have a product at this moment. I don't think anybody have a very compelling product. I mean, some company they do have a product that they said they will go into this market, but still, you do not see many of them are being used in the action. So there's a reason for that, right? So if the product is so good, then everybody will be using it, right? So which means I think the power consumption is still one of the biggest issues that we need to solve, right? For a market like this. So like handheld or set-top box or gateway, those areas, I think we know it's very high volume. But however, those areas, first of all, is very competitive, cost is very low, margin very low, and also there are a lot of ASSP available, right? So, but if there's an area we think there's, for example, is software defined or is flexible, then we think it will be a good value for us. Yes.
And the industry is seeing another big trend in. If you look at the market, you can see lots of OS now spring up, Linux based, or lots of OS now are coming out of the laboratory. So that's suggesting some big opportunity for and you competitive landscape for core process core develops mix now trying to MIPS trying to find a new area because the Linux is available. So really that's another big the sea of change in this industry. So the lots of OS are available in the market, and lots of the MIPS is now trying to enter in core process market for mobile phone. MIPS used to be just in a set-top box like but they kind of they kind of some you see of change. It doesn't mean some another opportunity for FPGA areas.
Yeah, I think the cell phone space, people definitely because of iPhone and iPad, right? People see the potential in those markets. But right now, those markets actually are served pretty well with ASSP and DSP. And people are looking for more information and more feature to be integrated into the phone. So, which means the performance requirement is very high. But yet, the requirement on the power is also increasing too. So, I wouldn't comment on MIPS, but I think I would say a lot of the processor company would definitely try to go into this market, but it's going to be a quite challenging and competitive market. I think what Xilinx goal right now is we try to go after those market which is underserved today. Underserved, which is not served very well with ASSP because they have the drawback. They don't have flexibility. It's not served very well with DSP because maybe its processing power is not high enough. In those areas, I think will be a good chance for Xilinx to go in, and then use that as a foothold. Maybe we can expand into the other areas, right? In fact, if you look at consumer electronic, even though predominantly FPGA is not found on handheld devices today, right? Maybe CPLD, but not FPGA. But on LCD or plasma display, FPGA has been very common, right? FPGA have been supporting most of these, 3D movement in the LCD display, and also as a timing controller, as a bridge of different interface, even as a processing engine in the LCD display. So we have customer that is using Xilinx FPGA in display today that we have been shipping millions of units. We're talking about 6 to 7 million units a year. This kind of quantity.
60.
Yeah, six or seven.
6 or 7.
Yeah. So it's not a very high volume if you compare to the cell phone, but it's very high volume for FPGA already. Yes. Yeah. Very high volume for FPGA. So, so that represents a very good opportunity for Xilinx, I think, in the embedded area. Right? People want, 2D to 3D conversion. They want frame rate conversion. They want, picture, video enhancement. Right? So all these features, you require a lot of processing power. Yeah.
Challenge time.
Well, I think it's also a very good time.
Yeah, good time.
Yeah, very good time. Yeah, because right now, as you see that many analysts company are expecting FPGA is posed to be a significant growth in the next few years, higher growth than the other semiconductor segments. So I don't remember the actual number, but I think it's outgrow the other areas. Yes. So we want to take the opportunity of this is what we call a programmable imperative, right? It's unstoppable. This basically the requirement from the market, the requirement from the customer. They want to do more with less. Everybody want to do more with less, right? You want to have more powerful product, but less power and cheaper, right? So these requirements and also differentiation. People, they don't want cookie cutter solutions. right? Maybe in very low-end white brand cell phone, they want a turnkey solution. But most of the customer today, they want differentiation. So FPGA will allow them to differentiate and go to market faster.
So FPGA is just the key factor for differentiation?
Yes, definitely, right? In fact, the reason that we are very successful in communication, because in communication space, they need flexibility, time to market, but they also need a lot of differentiation. So FPGA will allow them to develop their proprietary IP on the device. So this is a very good value of FPGA. There are a few technology changes, as you mentioned earlier, right? One is the limitation of the Moore's law, right? Moore's law said every 18 months your density is doubled. But our customer, were telling us that that's not enough. I want bigger parts. I'll give you an example. I think in our 65 nanometer technology, one of the product lines we call Vertex 5. The biggest Vertex 5 we have has 330,000 logic cell element. Okay, 300,000 logic cell element. If you look at our 28 nanometer technology, we call it Vertex 7, which is 2 generations later. Okay, 330,000 is a low end in the density. Our biggest device is 2 million logic cell. Okay. So the 40 nanometer, which is in between, our biggest element is 760,000 logic cell, right? So you can see that from 65 to 40, it grows from 330,000 to 760.
760. Yeah.
It's about double, right? But from 760 in 40 nanometer to 28 nanometer is more than double, right?
Quantum jump
is more than 2x. It's basically more than 2x kind of jump. So what is our challenge? Our challenge is customer is pushing us to have a bigger device. But Moore's law said you can only double within 18 months. So what should we do? So technologically, we basically develop these, what we call the silicon stack, silicon interconnect, SSI technology. Right? In fact, I have an opportunity to meet with Daniel in Seoul 2 weeks ago, or 3 weeks ago, right? We talk about this technology. It's a fabulous technology. It's basically having the stacking technology will allow you to put smaller die together to make it a big die. It's not a monolithic solution, but it will give you equivalent.
Looks like.
Right? So from the user point of view, they feel it is a big die. However, to Xilinx, we solve 2 technical challenges. One is we break the Moore's law. Right? In fact, we were joking the other day. We would say Xilinx broke the law. We broke the law, right? But it's not the legal law, but we broke the Moore's law. Secondly, is it will give us a better cost structure and yield, because we all know that in order to yield a bigger die, it takes longer time and it's more expensive. That's why the big die always come out the last in our family rollout. But this time, the big FPGA is composed of 4 different die, and the die is much smaller, which means what? Which means we can yield the die sooner and deliver the product faster to our customer. And also the yield is better and give us a better cost structure, which means the customer will have a better cost on the bigger FPGA. Right? So those are the innovation. I think that Xilinx will continue to invest to tackle the technical challenge. The second challenge is power. Right? Power is, as you know, right, very important feature, requirement from customers, from the government, from the customers, from everybody, from your supply chain. Everybody wants low power. But how do you make it low power? You involve many things. For example, the process technology will help you to reduce static power. But dynamic power, you require architectural innovation. So Xilinx, we have invested into many things. For example, like a gated clock. We have parcel reconfiguration. We have special design IOs that save power. We have different transistor threshold voltage mix, right, to optimize on power. We have all sorts of things. So these actually will help reduce the dynamic power. And then we have software tool to do power optimization. So all these actually helping our new family to improve power by more than 2x. So every family we look at, from the 40 nanometer to 20 nanometer, we reduce the power by more than 50%, which is very significant. But if you ask me whether we can continue to do that for every process node, I don't know. But it's a very big challenge. It's a very big challenge. Right? So I guess the other challenge is customer want productivity improved too. Right? We talk about performance, we talk about power, but productivity at the same time, the customer said, oh, you give me a big FPGA, good. You give me very good, power, which is good. But I want to do the design in half the time, which means they want us to improve the software runtime. They want us to improve the solution delivery time, IP delivery time. They want to migrate their IP from older technology to new technology faster. So how do we do that? Well, definitely the package innovation is one thing, right? So we have this package, but also we're looking at how we can unify the architecture. For our low-end and high-end device, if we can have one architecture, which allow customer to migrate from a smaller device to a bigger device faster, right? Because it's the same architecture. And vice versa, they can do a cost reduction from a high-end device to a smaller device. If you look at our competition, they have different architecture. Mid-end, low-end, high-end, 3 different architecture. But in our case, in 28 nanometer, we will unify the architecture. We will make sure that customer can migrate IP very fast. They can even migrate from 65 or 40 technology into 28 technology faster because it's using the same architecture. So these will mean improve productivity for our customers. And we're also looking at how do we build what we call the targeted design platform, TDP, which means we provide customer not only boards and reference design, but we package everything together in one open box experience. You open the box, you plug in the power, everything works. We built this, what we call the TDP, for specific market, wireless, medical, consumer, industrial. We have specific solutions for different market. And what the customer will get is they will get the development board, they will get a lot of daughter card. The daughter card will contain different interface for different applications. It will have the software, you even have the IP already loaded onto the FPGA. Have a manual. Everything is just plug and play. So Xilinx, we are the first FPGA company to do that. And we call it productivity improvement for our customers. So that they don't have to develop, for example, like memory controller and all these standard things again. Everything is already in the FPGA. Right? So Xilinx is really changing the concept of usability. And we hope we can help improve the design productivity of our customers. Right? But these are quite challenging to do. It sounds simple, but it's not. For example, all the boards that Xilinx provide can work with other company boards too. For example, you have a TI board, you have an analog devices board, you have a Freescale board. They can connect together seamlessly with our board because why we're using a standard interface. We call it a PGA mezzanine car, FMC, which is an industry standard. So all these solutions, we can put an AVNet or Makers board together too. We can, connect them together and make it a complete solution. So, but obviously those are the result of customer requirement and market challenge. Yeah. Yes, as DJ said, the technology concept is not brand new, right? We basically are the first one who applied this in the FPGA. The difference this time is, well, first of all, FPGA actually is a very high performance device, right? We're talking about the chip is running at 800 megahertz, and we have a lot of high-speed IOs, SerDes, and PLLs on the device. So we need to ensure, first of all, the latency between different slides is very short, right? So this is very key, the latency. The second challenge is we need to ensure it's very reliable. Okay, so that's why we use the concept of the silicon interposer. In fact, TSMC is the one who developed this silicon interposer.
Yes.
And with this silicon interposer, first of all, the silicon interposer does not have any transistor in it. Okay, so it's a passive. It's a passive. So because it does not have any transistor, it's very easy to manufacture. And it's also based on a 65 nanometer technology. It's a very mature technology. So the yield is very high. But the difference is it has a lot of wires in the interposer. So we can connect the slides together. Right? And then it also contains what we call the silicon via, TSV technology, that allow you to connect this die to the substrate, to the package substrate. The challenge is really how to increase the reliability of those TSV, and then also to fill those TSV with conducting material.
Okay.
And the techniques to do that is patented by TSMC. It's not easy to do.
Yes.
Because you cannot just dump your conducting material in. You need to consider reliability. You need to consider because it's etched. The TSV is a hole that's etched. It's not laser drill. It's etched. So you make sure it's uniform. You make sure it doesn't short circuit, right, your devices. The other technology actually is on the micro bumps. So the micro bumps are the bumps that connecting the FPGA die to this interposer. Okay, and the interposer will have the regular C4 bump connected to the package substrate, right? So on the micro bump, we need to make sure that is you have all the connections, and also can what do you call that? Sustain to the stress, right? So the good thing about it is the interposer is the same material as the die, even though it's different technology, but it's the same silicon material, right? So it will expand and contract at the same time. So that's why the stress on this microbump is kept to the minimum. But we still have to ensure that this microbump does not fall out or does not, during the contraction or expansion, it doesn't fall out, right? So the reliability of this microbump is a technology. The silicon via, I also mentioned that, right? Make sure that it's the etch process, everything is good. And then the interposer, this one is relatively easier, right? But we still have to make sure that it works well when you're putting everything together. Okay, so and then we also put these 4 FPGA dies side by side, and we don't stack them. The reason is because FPGA because it's very high frequency operation, so the power consumption could be high. So if you put it on top of each other, the FPGA die at the bottom, the heat cannot go anywhere. It can only go sideways. So by doing that, we can remove the issue. The other thing is, if you stack the die, you need to have a new design flow. Why? Because your signal may go horizontally, your signal may go vertically. And there's no such 3D tool available in the market. But if you put it on sideways, the signal still go from this die, going down to the interposer, up on this die, and going down, and up, and going down. So it's still horizontal, which means our software tool, design flow, we don't need to change. We don't need to change. So that was one of the innovation too. Yeah. So it's stacking, but it's not stacking different FPGA die, but stacking the die with the interposer.
Interposer.
Yeah. So it's 3D in that sense. So overall, these are the four main technology, and then this is definitely the result of multiple vendor that basically helping to make this SSI technology a reality, right? So Xilinx, we basically design the FPGA, we design the interposer, and we design the package, but we do not manufacture them. So we let TSMC manufacture the FPGA and the interposer and the TSV technology, and then the EBIDAN, they will provide the package substrate, and MCore will put all these things together and also provide the microbump. So the microbump technology belongs to MCore. Yes. So all these companies work together, we provide the final product.
Great.
Yes, I hope I have explained the detail enough.
Yes.
Yeah. So this is basically what I just mentioned on the advantage of this, right? So traditionally you have multi-chip. So not only that your trace has to go on the PCB trace, the latency is longer, and also you consume a lot of IOs. You do not have that many IO. I think the biggest FPGA device today is only have 1,300 IO. But in our FPGA, we have tens of thousands of connections, right? And the latency is only 1 nanosecond from die to die. So it's very, very short, very high performance. And this actually is the visualized how we put the four slides together, and then we have the interposer. You have all these connections between the die, and then you just stack it over it. Yeah. So that's how we make.
So you can get good performance and high speed.
Yes.
And low power
at the same time, and then without changing our tool.
Yeah, and large gains in productivity.
Yes, yes. And then did I mention this yield curve? Right, this yield curve is also quite important. Actually, I showed it to Daniel last time in Seoul. Right, traditionally the yield is in proportional to the size. So the bigger the size is, the lower the yield, right? So in order to yield a 2 million logic cell die, your yield will be all the way down here. So as the process improve, your yield may improve, but the curve will still look like this, right? If your FPGA size is very big, your yield is still low compared to the other size. But what we do is, instead of using a monolithic die, we make it 4 smaller die, much smaller, right? So it's only 25% of a 2 million logic cell. So we make it smaller, which means the yield is what? Improve that much, right? So we can only yield a die this small. The yield of this smaller die is much higher than the yield of this die.